Okay, so yeah, before talked in our slide before, let us see. I told you about why we need to start with ring star networks. I told you, like in the previous slide, I told you about the star network, which it is a star network because you can see there is a central node over here, and it transmits information to all of its, nearby nodes. Okay, like in a star fashion. So it's a star network. Okay, in the same time, then I, after many years, I thought like, why not? We can do a mix of two networks. That is why these two nodes shall remain separated. So then I thought of connecting them like in this fashion. So if you see, if you connect in this fashion, then it is like a ring network, and the previous structure was a star network. So this amalgamation of two different networks is known as a ring star network. Okay, so which we thought and was mentioned for the first time. Okay, so no one ever like before us had reported this network, Ringstar network. So then we thought like what dynamics or what network properties this system has. So then this was done with one of my colleague from Greece. And here in this study, we actually studied what is the significance of considering ring star network. The significance is when you want, you can have a ring. When you want, you can have a star. When you want, you can have a ring star network. So just changing the remote or changing the parameters, you can just traverse from one network to a different network. So just this network, ring star network, gives the benefit of three different networks based on the three different networks based on the different control parameters. So that's the advantage of this ring star network. And what is this chimera state? Okay. As some of you told, like who are doing the mini project, they know about it. So chimera states are something like it has a combination of both synchronous and asynchronous states. Okay, that means as I told you, out of 15 students, maybe 3 students are not able to are out of the sync, and maybe 12 of them are in sync. Okay, so it's a combination of both synchronous and asynchronous behaviors. And and it is in a network where you have all identical nodes. You can also get that in non-identical nodes, but usually the definition is concerned about the identical nodes. Okay, and in some network topology, you need to have a network. So if I ask a question that these are all the nodes, and can we have a chimera state? No, definitely not, because there is no network associated. There is no nodes. So if I tell you, yeah, can we have a chimera state in this network? Then I can say yes, it might be, because it's a network, and there can be full synchronization. There can be total asynchronization. There can be a coexistence of synchronous and asynchronous behavior, chimera state. So most commonly studied chimera states are frequency chimera states. Okay, frequency, something known as a frequency chimera. Uh, and they are usually distinguished by the difference in the frequencies of the oscillatory elements. Okay, if you have difference in the frequencies, all frequencies are not same. Some frequencies are same. Say out of 15 students, like each of you are oscillator actually, and I am actually the main oscillator talking about here. So it's like this classroom is a star network, because whatever I am saying, it is going to each one of you. So it's like a star network. But if trying to understand also, that becomes a ring star network. Anyway, so all oscillators or all fireflies, you can imagine. When I'm saying oscillators, you should imagine it like a firefly. Okay, all oscillator, like each firefly has their own frequency. You have your own frequency. Okay, so that doesn't matter. The original frequency doesn't matter. It's the coupling what matters. Okay, depending on the coupling, you can have chimera states, you can have synchronizations. Okay, behavior. So you can see the coupling in between them. Just okay. So all oscillators have their own intrinsic frequency, that is the original frequency, but it is the coupling between the oscillator what matters. Okay, so the coupling when it is introduced between each of the oscillators gives you a distribution of frequencies. Okay, and therefore you see the emergence of chimera states. Emergence of chimera states is not a magic. Okay, it's due to the coupling in between the oscillators. Okay, so therefore, this is the reason why the chimera state are very non-trivial and unexpected actually. Okay, before it was discovered, it was highly unexpected. Before it was discovered, it was highly unexpected. Okay, after it was discovered, a lot of people started observing it. So Kuramoto and Batog, like they observed these patterns for the first time in phase oscillators as an attempt to understand this mathematically. So synchronization and these aspects are important. You need to understand them. Why? So this paragraph relates why you need to understand them. Actually, they are related to this neurological disorders. Like you can see epilepsy. You can see that epilepsy. What researchers have found in medical grounds is epilepsy is not only a like a dynamical disease which occurs with time. Like you can see, epileptic means like somewhat you get those feeds, epileptic feeds, and then it goes, and then again suddenly you will get it. Okay, that's what epilepsy is. So it is a dynamical disease. That means varies with time. Varies with time. At some time you will have that feed. After a while it will be okay. Again you might have it. Okay. Might not be periodic. Might not necessarily be periodic. But they found that it is not a dynamical disease, but also it's a topological disease. That means it depends on the type of the connection between the neurons in that particular individual. Those who are having the epilepsy, you can take. Those who are not having the epilepsy, you can take. Study the interconnection between each of their neuron in the brains. You will find the topology in what the neurons are connected will be different in both of the cases. Okay. So therefore, epilepsy is not a dynamical disease, but also a topological disease. It depends on the network of neurons connected in that individual's brain. Okay. So yeah, some applications I should have told this before. The star and ring networks are common, like you can see in hub systems, social systems, or even in computer networks. Okay, I think you can get this when you connect the LAN wires. There is a tab, and you put one LAN wire, and there are five ports coming out. You can connect to 5 computers. Okay, that is an example of a star network that look like a box, but actually it's like a star because you are giving one from to multiple. So you can see like the information flow in that can transmit securely. Okay, else there can be a compromise in the security leading to cyber crimes. Why it is secure? Because of the Chua circuit, because of the chaotic property exhibited by the Chua circuits. Chua circuit can give you chaotic signals which have been proven to be useful in many cryptographic systems. Okay, so that's one of the reason why you need to have Chua circuits in each of the nodes when you are delivering the secure information in a computer. Anyway, so um, yeah, okay. So this is the actually how the ring star networks looks like. Okay, so you can see this is a Chua ring star network, and this is from the paper actually, and I'm considering around 300 nodes. I'm considering around 300 nodes here, and you can see this is known as the central node. This is known as the central node, and these are known as the peripheral. Sorry. Hmm? Did you imagine something? What is? Okay. So this is the central node and these are the peripheral nodes. Okay. So you can see this is the dynamical equation of the network. Okay. So this is the coupling term actually. And due to this coupling term, actually you will see a lot of network dynamical phenomena. So for the central node, I think Miss Arya has already known about this, I think. Does it make sense? Yes. So for the central node, the dynamical equations are this. Okay, don't worry about the equation. It is just completely intuitive based. It's not like heavy mathematical equations, but you just have to follow it. And these are the Chua's equations, Chua dynamical that circuit equations. Okay. And when you simulate it, when you simulate this circuit, like the dynamics, you get something more interesting over here. Okay. Something more interesting in the sense that you will see, let us consider this one, you will see something known as the single well chimera state. Okay, single well chimera state. Why it is known as single well chimera state? Any ideas? You can see that this well, all positive, above zero, everything lies above zero. Okay, everything lies above zero. Okay, so all the dynamics is above zero, and hence this is known as a single well chimera state, right? And yeah, so this you can see lot of colors. These are all colors, all 300 different colors. 300 different colors. You can, yeah, there exist only 7 colors, but I have taken many shades to show them. Okay, so here I have taken 300 different, so I have taken the dynamics of each of the nodes. Okay, so this is how single node, single well chimera state is there. And I have taken one node, any one node, single node. This is the dynamics of a single node. Okay, you can see it is clearly above zero, and they are oscillating in between two states. They're oscillating in between two states. Okay. Fine. So this is known as something known as single well chimera state. Now, an interesting phenomena we saw is something known as a double well chimera state. Okay. You can see that it is now traversing the negative values. Okay, both negative and positive. Both negative and positive. So it stays in negative and stays in positive. And this is all 300 nodes we have plotted, all 300 nodes, and this is a single node. This is a single node. Okay, this is just a single. So the idea is why it happens. Can you tell? You saw some single well chimera state, you saw some double well chimera state, but why it is like this? Those who give the Chua talk can tell. Any ideas? Why? At least can you see that this negative, sometimes negative, sometimes positive is happening? Can you see why? You can see it. Till now, this question is open. Till now, this question is open. I could not think of it actually, but there is a hypothesis in my mind which can be true, but I have not tested. Okay. Why this single and double well chimera state can exist? Okay. Let me tell you. Let me show you the picture. Can you see this picture? In this picture, this guy is also going from negative to positive. Okay, that means the oscillators, they take the positive values and also they take the negative values. Okay, because of this Chua's attractor. Okay, the double scroll. This is known as a double scroll because you can see two scrolls over here, double scroll attractor. But it takes both positive and negative values at the same time. Okay, so therefore it doesn't it's not surprising to you that why like it should not be surprising that here it took some negative values and positive values. Okay, so therefore due to the topology of the chaotic attractor, you can see this chimera state, this type of chimera state. So if it was only a single scroll and lying only on positive axis, then I can surely say that never the neighboring elements of the node also go to negative values. They will stay in positive. Okay, so therefore that is one of the uh, hypothesis I have, which I don't know yet is true or not. So you can see this connection between the double scroll attractor. The open question is because the double scroll attractor also takes positive, traverses between positive and negative, therefore this state is also traversing between positive and negative. However, you can understand that these two are totally unrelated things. Okay, totally unrelated things. Here I am talking double scroll attractor of a single node, okay, but this guy is of a coupled system. So these two are totally different things, but do they interplay with each other? That is still not understood. Okay, maybe it will be clear within future times. So this is what it is. And what is a chimera? What is a chimera? Yes. So chimera is actually a Greek word. Chimera is actually a Greek word. You can see from Wikipedia over here. So any mythical or fictional creature with parts taken from various animals. Okay. So that is what is a chimera. And to say you that, therefore, chimera in dynamic system also means that there is a coexistence of synchronous and asynchronous nodes. So you can see that here in this example, you can see that, oh no, what happened here? Uh, yeah, this is a chimera state. From this picture, you can see that this is a, this is, yeah, but this guy, yeah, this is line of, this is a, this is a line, and ah, this one, ah, dragon, okay. So you can see these three parts are together, and it's actually from Greek mythology. Okay, so this is what is known as a chimera state. This is a chimera. So this is just an idea of the presence of both synchronous and asynchronous state. Okay, two different states together. Anyway, so this is what it is. Yeah. So you can see like it has been found that chimera states have been involved and are deeply connected due to to show us the cause or the mechanism behind many neurological diseases like schizophrenia, Parkinson's, brain tumors, and many others. Okay, you can just go into the like experimental studies over there and find it out. Is the case. During some experiments, some scientist, Tognoli, also reported this presence of both synchronous and asynchronous activity during your left and right finger movements. Okay, so sometimes your left finger movements are synchronous and your right finger movements are not synchronous. So these are the events where you can see that chimera states can be observed. Okay? And even it is there with the sleeping pattern of these aquatic animals where whales and dolphins they keep they are not asleep all the time. So one of their eyes, one of there are two brains, like two hemispheres of the brain. One hemisphere will be active, other hemisphere will be sleeping. Okay, so you can see one is at a rest state and another is at a like a dynamic state, active. Okay, so don't think of attacking them thinking that they are asleep. Okay, they know you that you are coming. So yeah, so if you want to read more about fireflies and the sink, you can read it from the Quanta magazine. It's a very nice magazine. Those who are interested in science, okay, so you can get to know many up-to-date facts from here. So how do fireflies actually flash in sync? Okay, so synchronized flashing in fireflies confirms that a novel form of chimeric synchrony occurs naturally. It was written by Joshua Sokol in 2022. So you can imagine that these synchronous states, synchronous dynamics, chimera states are still evolving topics. Okay, I strongly suggest you to read this Quanta magazine article. So this is just a part of the firefly I have taken in Zoom, showing where the light comes from. Okay, so yeah, so this is just an example. The link is over here. Yeah, so again, some studies continuing, like very novel phenomenon have been seen so far. Like those who have given the Vanderpool oscillator example. So this is an example taken in the VDP oscillator, or you can see in terms of heart dynamics. Okay, so you can see that this was done with some of my colleagues from Russia. But yes, they are like they found this actually phenomena, like they saw with the time step, like there is a traveling wave, and with time, this is time axis. As you increase time, chimera states takes in, and the time is quite high, 9 into 10 to the power 5. It's not like you are starting from time t equal to 0. So even in the time, in the long run of the time, the states are still transitioning between each other. So these are totally computationally based. So yeah, anyway, so what we found is what is the relation between the transition between different chimera or solitary states to traveling waves. So like Miss Ari, I suggest maybe you can think of this. Okay, so maybe like you are seeing two different kinds of traveling waves. So try to see, like, are you getting any chimera states, if any, like how they transit to traveling waves, different types of traveling waves. So yeah. Anyway, so different studies are there. I'm just trying to show you these pictures mainly because to appreciate that these are highly computationally simulation based simulations. Okay, so you know that we learned about a ring network, isn't it? We learned about a ring star network. Now another network can be is a lattice network. Lattice network in the sense you have this lattice. Okay, this is a lattice. Okay, and you can think of this as 50 cross 50 lattice, like elements will be there, so 2500 nodes interconnected, coupled with each other. And if you simulate those, then you see these spiral patterns, different kinds of spatiotemporal patterns. Okay, so these are the different patterns you can see. This is something known as a synchronous state. All are in one color. This is like when you drop a stone in the river, you see those waves, target waves, repelling out of, like as these repelling structures. Okay, and these are known as like the traveling, like the spiral waves. Fine, and these are something like chimera like states, chimera states, in the sense that these are something like you can see. Blue means kind of synchronous, yellow means they have more values, and here these are solitary states, mainly because all are in yellow color mostly, but there is a tiny tinge which is adamant and lying in that particular shape. So this is known as a solitary. These are like fixed. Okay? These are solitary states. Fine. So, but this guy, observe this guy and this guy. Okay, they are totally different structures. Why? Can you observe? Can you see what's the difference between the two structures? In the first structure, you can see the center is quite unique, like unique center, but here there is no center at all. In the below part, there is no center at all, because you can see that there is a collection of different colors over here. Okay, so therefore this is like a spiral, but you can see that this is a spiral wave chimera. Spiral wave chimera. Okay, fine. So yeah, yeah. Actually, I found that I am consuming a lot of memory in my computer. I have to free it up. Okay. So this is a very nice image of this spiral wave over here, or a chimera. You can see it's a chimera because a lot of different colors you see on the center. Okay, this was taken from a uh, like German website, like during some conference I have taken it. But anyway, so it's fine. But yeah, you see all these spiral waves and all, but you can characterize all these spiral waves by using some different characterizations, something known as root mean square deviation. These are all characteristics. Just like in data analytics, you learn about normalization and all this. It is a way to characterize all these different colors of the spiral waves. Okay, so root mean square deviation, all depending on the nearby nodes. Okay, you take the difference, so it will tell you how close the values are, and you take the root over that. Okay, and most importantly, delta will be calculated as an average over the time. Okay, you take the average of all the nodes and see how they go over to understand how each are deviating from each other. Hmm. So this is a target wave because you have these waves going on, but at the same time you can see these dots. You can see these dots. Okay, here also there are a lot of dots. So therefore, it's a solitary state as well as it's a target. Okay, so it's a kind of like solitary state chimera pattern, you can say. Fine. Uh, so anyway, there are other coefficients which I don't want you to go into detail, but it's okay. Like something known as like a cross correlation coefficient. Okay. So cross correlation coefficient, you can see. I think cross correlation coefficient you already know, isn't it? In analytics, no. In statistics, no. What? Yeah, I think it's telling to. Yeah. Anyway, so just know about this cross correlation, and yeah, you can see these patterns, and you can see why this pattern is different. So you can see all are in one color, but this guy is in a different color. Okay. When you plot these oscillators, you can see that they actually occupy two different phase portraits. So it's not a magic. It's dynamically characterized. Okay. Since there are two different population oscillating differently, therefore you saw this pattern over here like this. Okay. There are two different patterns, and hence there are two different two phase portraits. And it's like a solitary state chimera. Fine. So more details you can find how to quantify these transitions from spiral waves and to spiral wave chimera. There are a lot of different like detailed characterizations which will not go in this class. But yeah, they are a bit technically involved. But just know this is known as a rise frequency, and this is something known as a finite time. Like how can I say this? You can consider this as a what you I think it is known as LIF. I forgot. Yes, you can call it as this index of local sensitivity. You can call this as index of local sensitivity. See, this is a chimera state and there is a disturbance in the center, but how can you characterize it? If you use this method, then it tells you this there is a disturbance in the center. Okay. So these are some characterizations, but I don't want to go into detail. Moreover, you can understand not only lattice, but in terms of multiplex, like multi-layer networks. There can be layer over layer. Like you can understand, like now graphene is so popular, isn't it? Graphene is so popular. Graphene is carbon elements, right? And they have their own multi-layer structures. So you have to understand these. This is layer one. This is layer two. Okay. So how these dynamics happens? How one layer competes with another layer. Okay, so here I have taken one example. Layer 1 exhibits these spiral patterns. Here you have spirals, but in layer 2, suppose you have these